All right, I'm going to keep moving on here. So at this point, we've covered a basic birth-death model and a predator-prey model. So these are models that you would cover in your dynamical systems classes that you might take. But we've talked a lot about simulation of biochemical systems, especially Linda gave us a great introduction on how those work. So I'd actually like to show you one of those models. And the model I'd like to show you, is the genetic toggle switch. So let me go ahead and scroll down here. Okay. So the genetic toggle switch so this is the is from the Gardner, Kenner, and Collins paper back in 2000. And this was it was designed and constructed in a synthetic bacteria gene regulatory network. The idea is that it's a building block for a single memory unit. So it's a toggle switch. So it's either on or off, right? And then you have colonies of these, and they can make up then much larger sets of things. And exterior chemicals would come in and switch the specific things under direct conditions. So this was an experiment to do with the basics of synthetic biology. The basic idea is that you have this, your DNA here, and on that DNA, you've got one protein here that's a promoter 1, and one protein here is a promoter 2. You can see they're in opposite directions. That's their transcription direction. And the idea with that is that promoter 1 is transcribed that way, and along with promoter 1, repressor 2 is transcribed. So basically, promoter 1 represses promoter 2. Promoter 2 has repressor 1 transcribed along with it, and that inhibits promoter 1. So you've got this double negative feedback loop. And then all you need to do is knock out one of those loops, and it'll flip high or low. And then there's a reporter there that tells you what's going on. So the idea then of this cartoon model is that we want to make a mathematical model. So we're going to call promoter 1 U, promoter 2 V, and we're going to say that the creation rate of U is inversely proportional to V, and the creation rate of V is inversely proportional to U, to the current concentration of U or V, and that U just degrades sort of monotonically, and V degrades monotonically. So those are our basic ideas. That's our mathematical model. Now we want to take that and make that a nice computer model. So to do that, we have to convert our ODE into individual mechanistic reactions. Now, this is the piece where a lot of people who are using StochSS start to get hung up. They're used to maybe looking at everything in terms of reaction rate equations or differential equations, such that the rate of change of my variable here is equal to some sort of equation here. But the way stochastic simulation works is you're looking at individual mechanistic changes, right? So you create one U, or one U goes away. You create one V, or one V goes away. And that means we have to decompose our ODE into individual reactions. And we're going to decompose it into 4 individual reactions. So if we're just looking at the U, the action that happens is either we start with nothing and we make a U, or we have a U and that U degrades and goes to nothing. So those are the 2 actions, and the rate at which these 2 things happen is exactly what's in here. So the rate that you create a U is alpha 1 divided by 1 plus V raised to the beta power. And then U goes to nothing is exactly that, it has some number in front of that number happens to be 1. 1 can be multiplied by anything. So changing this du dt equals alpha 1 over 1 plus V to the beta minus U into these 2 different reactions is an important piece of understanding. Now we can do the same exact procedure to the V equation, right? So we have a creation mechanistic interaction for V, and we have a destruction mechanistic interaction for V. So we put that all together. And we can create a new population well-mixed model. That population well-mixed model is going to have 2 species, U and V. We can give them an initial value. Turns out the initial value doesn't actually matter that much. So we can have 1 or 10. We're going to define 6 different parameters here. Alpha 1, alpha 2, both equal to 5. Beta 1, beta and gamma, both equal to 2. And then mu is our destruction rate. We'll leave that the same. And we're going to define 4 reactions: creating U, destroying U, creating V, and destroying V. So I'm going to go ahead and escape out of this. Keep this on the screen here while so back to here. We're looking at our SIAM mini tutorial project. I'm going to go ahead and add a model, new model. That model is going to be genetic toggle switch. And I'm going to make this, I'll make it concentration to start out, as I always do. So looking at add variable, we're going to start out with U, and that's going to be initial value 1. We're going to add another variable. This is going to be V, initial value 1. Both concentration, great. All right, then we just need to define 6 different parameters. Just go ahead and click that 6 times, save us a little time here. So our parameters are alpha 1, which is 5. And then the second parameter is alpha 2 at 5. And then we have beta at 2 and gamma at 2. And then we have mu. I guess we're 1 over. That's great. I guess in other versions I have mu1 and mu2. They're the same, so it's not really necessary. And it's easy. I'm just going to click this remove button here. And now we're down to 5 parameters. No problem whatsoever. And then, just to show, sometimes this annotation is really nice. Annotation, so this is the alpha 1 parameter. Hit OK. And that annotation will be very helpful. In the future, we plan on having a way to publish these models in a way that is easily viewable and distributable. Okay, so 6 parameters, okay, in our case 5 here now. And we're going to define 4 reactions. Okay, so expand the reaction. And I'm going to add a reaction. You can see create U and create V. Those are both going to be type custom propensity. So before I used just the standard reactions, and then last one I used custom mass action. Now I'm going to use custom propensity because this rate is not mass action. It is not a simple numeric number, so I can't necessarily use that. So I have to use custom propensity. And I'm going to call this create U. Let's see, it is going to be, just delete that. So empty set goes to U, right? That's empty set goes to U. And the rate that I want to put is this alpha 1 over 1 plus V to the beta. So the reaction type is custom propensity. Now, I just put an expression in here, and you can see this is the custom propensity evaluated for the reaction. So you can really put any mathematical expression in here. Now, of course, any mathematical expression means you're going to have to know exactly what kind of math that's going into there. And one of the issues with this is you're raising something to a power. So you're going to have to use the pow function that you might use in, say, Python or C. So to put this together, it's going to be 1 divided by the quantity 1 plus pow, and then it's going to be V as the first argument here, and then beta is the second argument. And then got to make sure you close all your parentheses, very important. So that is going to be the rate of nothing goes to U. Custom propensity, perfect. I'm going to go ahead and do another custom propensity because this is going to be create V. Create V is going to be the same thing. So I delete my reactants there. I'm going to make a V instead of a U. I'm going to put a 1 divided by the parentheses, 1 plus pow. Now in this case, looking over here, you're going to see this is going to be, oh, I'm sorry. I'm missing my alphas. alpha 2 divided by 1 plus pow. This is going to be u and gamma. So u comma gamma. Parentheses. All right, so we're making v's at that. I'm going to click back over here, and this actually has to be alpha 1. All right, so those are my two custom propensities. And then, A goes to nothing. That's fine. We can do add reaction. A goes to nothing. This is going to be the destroy u. That's going to happen at rate mu. I'm going to add another reaction. A goes to nothing. This is going to be destroy V. Select our reactant V. So we've got V goes to nothing. I click save reaction, and now you can see all of these. And let's just double check this is all working correctly. Alpha 1 over 1 plus V to the beta. This is alpha 2 divided by 1 plus 1 u raised to the gamma power. And both degrading at mu. Oh, see, this one is wrong. So let's go back here and make sure we select the right thing. Save reaction. Okay. Now we've got that all working. Great. Leave this all alone. Simulate, preview. So we start out at 1 and we go to 1.5, and you can see u and v go together. Now, this is actually part of the point. A deterministic continuous simulation cannot really effectively simulate a toggle switch situation. So I need to go back up here and change my concentration back to population. And then I'll click simulate again. Okay, so now you see we start at 1, but now we have a much different dynamic. So the difference between these two different simulations, I think, is one of the most important pieces when you think about stochastic simulation. So in this, now the toggle switch is defined to be equally flip-flop, and I've tuned the beta and gamma parameters to be so it'll flip, but not all that much. If you increase beta and or gamma, it'll stick much more strongly in states that it already is. And by states, what I mean is you can see that we're either in a V-dominated regime or in a U-dominated regime, but we're never in the case that both V and U are high. So here, between basically time point 2.5 and time point 6.1 over here, we're mostly in the V. We get a little bit of U, but then it goes away. And then we get the V gets low enough and U gets high enough that we're able to switch over, and now we're in a U-dominated state for a short amount of time. If I click simulate again, I'm going to get a much different simulation. So now we only have two different regimes. It starts out heavily in the V-dominated, well, it starts out in the U-dominated regime, switches very quickly to V-dominated, which it keeps until right about 10, 9.9 it looks like, 9.8. And then we get into a U-dominated regime. Oh, and then you can see that I zoomed all the way out. So let me try to do this again. Yeah. No. Auto scale. There we go. Okay, so there's lots of features over here that you can help. If you have more questions about Plotly, please take a look at the documentation. So here is a simulation of the genetic toggle switch running back and forth. So we can run through a bunch of different ones here, but what I think is most interesting now is to look at our parameter sweep workflow. So the parameter sweep workflow, what that means is I would like to see how this simulation varies as I vary the parameters. And parameter sweep settings, there are two types. You can either vary one parameter at a time or two parameters at a time. I'm going to choose two parameters. You have to choose some variable of interest. What is it that you're looking to measure as some sort of output of this simulation? And sweep variables, I'll just choose alpha 1 and alpha 2. It's not possible to choose these both to be the same. The current value is 12, so I'll say, well, a minimum of 2.5, maximum of 7.5, and 11 steps. These are just the defaults. And what this means is that there's going to be, a grid that's 11 by 11, and the one corner is going to be 2.5, 2.5. One corner is going to be 7.5, 7.5, and then the opposite corners will be the opposite of that. So you're looking at a grid of parameter values, and each point in that grid is then going to be one simulation, and we're going to look at the values of that simulation. I'm going to choose this to be SSA. I'm going to run not one simulation per parameter grid point, but 20 simulations per parameter grid point, right? Maybe a single simulation isn't actually going to give you anything very interesting, so you need to run all these together. So I will click Save, and then click, and then I'll click Start Workflow. So that changes all of these things now to, I can't change them anymore because it's running. And then after just a short amount of time, I can say, well, I can look at my variable of interest. I can look at feature extraction. So what do I mean by feature extraction? So how do I calculate a value, a single value, from a population concentration data of a simulated trajectory? So I can look at either the population at the last time point, the variance of the population, the average of the population, minimum or maximum population. And these are just sort of the ones we have in here now. I'll show you in a second how we can go further than this. And remember, if we ran 20 simulations at each one of these grid points, so we need to somehow aggregate that data together, aggregate the feature. So I'm going to take the average of these ensembles, and that gives us this. So here's our grid point, and you can see the value at each of these ensembles, and that value is the population at the last point of the variable u. I can also do average of the population, and that gives us a slightly different thing, but you can still see the grid there. So, and if I do V, you can see it's completely inverted, right? So if I have a low alpha 1, alpha 2, I'm going to get this grid point here, and this will give me this grid point here. I'll return to project, and now, so that's the genetic toggle switch, and I'm going to do a 2D parameter sweep. I know I went through that really quick. Sorry, I clicked on the workflow, and then I came to this page here, and I clicked 2D parameter sweep, and that did everything we talked about before. It created a new Jupyter notebook. It built this model from the model that we had built inside there. And then let's see, I'm going to run this. So I run these. I create my model, genetic toggle switch. And then I can configure the simulation, so it's probably exactly the same. So we're choosing the variable SSAC solver. For our simulations, we're going to do 20 trajectories. And then here is the interesting piece, right? So whenever I do a parameter sweep for a scientific project, the aggregation and feature extraction functions are usually the most important parts, and usually they're not simple as the last time point. So here, I said population at that lamp point. Well, what do you want to extract from the trajectory? So if you want to just change whatever's in here, that will work. And then aggregation function, average ensemble, that's what we had chosen before. Here we're just doing an average of whatever data comes in. And then our 2D parameter sweep, here, so if I do our 2D parameter sweep, we are going to run and plot these sort of things together. I can just run these. This might take a minute or so, or 5 seconds. And you can see here that we have a plot that is very similar to the one we had before. It might look different, but it's actually just flipped along the horizontal axis. If you look at just how the numbers are gone here. And then we can use plotly, then this looks pretty much exactly the same, right? 0 to 7, 0 to 7. So here is our parameter sweep notebook, 2D parameter sweeps, and allow you to customize your aggregation and feature extraction functions to do whatever it is that you need to do to pull out of your simulations. great. At this point, I would usually ask if anyone has any questions thus far. Okay, I guess I think I will just keep going. Slash of generic toggle switch, and I've got some nice